Let's say that you got this algorithm called calculate, and you come up with 3 different implementations for it, and you're trying to decide which one to use. One thing you're going to care about is how fast each implementation is. But, an algorithm doesn't possess speed as like a property. You can't say that like 1 has a speed of 10, 2 has a speed of 5, and 3 has a speed of 20, and say that 1 is better than 2 and 3 is better than 1. You can't do that. What you have to do is you have to look at how fast each algorithm is as a function of its input size. And if you can construct a graph like this, you can compare and contrast all of them and decide which one to use. So I want you to note that it's not the case that any one of these is always better than another one. So you might be looking at implementation 2 and seeing that it's lower down than these other ones and thinking that 2 is the fastest one. But then once you get to this a big enough input size over here, 1 starts to become faster than 2. So there's no real definitive answer, at least in this case, as to which implementation is fastest and which one you want to use. So I'm sure you can see that you'll be interested in graphs like these. So you're probably wondering, how do I construct a graph like this? And I'm going to show you. That sounded a lot like an infomercial. Excuse that. But let's say that we've got this function called sum of array. And what it does is it takes an array and it returns the sum. So if I gave an input of 1, 2, 3, the function would return 6. And we want to know, how fast is this as a function of its input size? Well, what we can do is we can see how many operations it takes to execute this algorithm. And we can assume that, let's say, it takes the computer 1 millisecond to perform one operation. And so from there we can infer how long it'll take to complete as a function of the input size. So let me show you how to do this. So what you want to do is you want to go through each line of code and say, how many operations does it take to get rid of this, to execute this line of code, and how many times is this line going to be repeated. And when you do that for each line of code, you can, you'll end up with your answer of how many operations it takes, and from there you can infer how many how many seconds does it take, or milliseconds. So let's do this. This first line of code here involves a variable declaration and an assignment. And let's say that that takes 2 operations. And this line of code is going to be executed once. There's no loops or anything that's going to make this be executed more than once. So 2 operations and 1 repetition. The second line is the same thing. It's a declaration and an assignment. So let's say 2 operations and 1 repetition. This third line of code involves 1 operation to get the length, well, one operation for the declaration of this variable n, 1 operation to get the length of this array, let's say, and a third operation to assign the length of the array to the variable. So this involves 3 operations, and it's repeated once. Let's move on to this line here. So this involves only 1 operation. We're just comparing I and n. But this line of code gets executed n plus 1 times. So it gets executed n times, while I is less than n, and 1 more time when I is equal to n. So here we've got 1 operation that's repeated n plus 1 times. Now let's look at the next line. Here we have, it takes 1 operation to access the ith element, 1 operation to sum these 2 together, and then a third operation to assign it to the sum variable. So this is going to be 3 operations, and it's going to be repeated n times. Moving on, this line of code involves one operation, and it's also repeated n times. And finally, this last line is one operation, and it's going to be repeated one time. Okay, so with all of this information here, we know how many operations this algorithm is going to take as a function of the input size, n. And doing a little algebra here, let's see what we get. We've got 2 plus 2 plus 3 is 7, plus 1 is 8, and then we've got 8 plus 3n and 1n is 4n, plus n plus 1. So we have 5n plus 9. And there you go. So we went through, we looked at how many operations each line takes and how many times each line is repeated, and now we have a function that tells us how many operations this algorithm is going to take as a function of the input size. And by doing this with the algorithms you write, you can construct a graph like this. And, you know, like I was saying before, once you have this graph, you can make a decision as to which algorithm you want to choose. And let's think about that. So, we know that implementation 2 is actually always better than 3. If you took game theory, you'd think about a strictly or strongly dominant strategy, I think it's called. So let's actually get rid of that, because this is what I do in real life. And now the question becomes, what input sizes do I care about? Because implementation 2 is better than 1 for input sizes smaller than this right here. But implementation 1 is better for input sizes that are past this line here, to the right of it. So if we're going to have a bunch of input sizes that are, you know, the majority are going to be less than this line, and that's what we really care about, we might want to choose implementation 2. But if we're going to be having some input sizes that are greater than this line, we might care more about 1. And honestly, in the real world, this difference here, so like the difference in this number of really milliseconds is, or even like nanoseconds, it's going to be really small. So it's almost trivial. Like, you don't have to even think about it. And so if this line right here kind of continued on, this is really good performance. But if this one carried on, it's going to keep going up and up and up. And for an input size like over here, you're going to start to see like a really big difference between the two implementations, to the point where 2 becomes so expensive that it's almost unusable. So we often care about these worst case situations. We want to have an algorithm that supports large input sizes, and here 2 seems to, you know, not really even be plausible for a big input size. And that's a great segue into asymptotic analysis. So asymptotic analysis is about looking at a function as the input size gets to be really, really large. So let me go to Wikipedia here. So you can approximate a function f. So you can say that f is approximately g as n gets to be really large, as n tends to infinity. And there are some rules for how you do this approximation. So if you have a function like this, where you've got 8x squared plus 3x plus 7, if you want to asymptotically approximate this, what you do is you first drop off the lower order terms, because as x gets to be large, they become insignificant. And you also drop off the coefficient before the highest order term. So you would say that 8x squared plus 3x plus 7 is approximately x squared as x tends to infinity. And actually, let's change this to n here. One moment. Yeah. So, I mean, we could go through functions like this each time and figure out precisely what the function is that describes how many operations it takes. But as you saw, it's a little bit time consuming. And if we can approximate it, that'll save us time and basically get us the same result. So instead of looking at this here and this here and even in here, we would just look at the highest order term, quote unquote, of the algorithm. And in this case, the highest order term is this while loop from 0 to n. So we would say that as n tends to infinity, this can be approximated by the function n. And to give you a different example, if you had, let's say, a function that has its highest order term is a for loop from 0 to n with another for loop nested inside from 0 to n, this function can be, assuming that this is the highest order term, this can be approximated by the function n squared. And if there was another one inside here, it can be approximated by the function n cubed. And yeah, I won't go through all the examples, but the idea is that instead of going through everything and it's time consuming to go through everything, you can just focus on the highest order part of the algorithm and approximate and do an asymptotic analysis. And to show you visually why we do this, I graphed these three functions. So I've got functions 1 and 2 are of the same order. Their highest order term is x, and function 3 has the highest order term of x squared. And what I want to show you is that the difference between 1 and 2 is a lot greater than the difference between these guys and 3. So let me put it this way. If you have, I don't know, the difference between the two highest order function 1 and highest order function 2, we take the difference between these versus the difference between same order function 1 and same order function 2 with different coefficients, let's say coefficients a and b, as the domain gets to be large, as n gets to be large, the difference between these guys is always going to be a lot bigger than the difference between these guys. So being that we care about how things perform as the input gets to be really large, we kind of, we only care about the most important things. And we do an asymptotic analysis where we approximate what the function looks like. So now I want to talk about big O, big omega, and big theta. And you've probably heard of big O before, but you might not have heard of big omega and big theta. And essentially, these are math terms. Mathematicians have been using these before computers were even invented. But now computer programmers and computer scientists use these terms to analyze their algorithms. So let's jump into it. So big O. Big O is an analysis of how something is going to perform in the worst case. And if we have a function f of x, and we also have a function g of x, and g of x is always going to be bigger than f of x, we know that, like, in the worst possible case, f of x is at least going to be lower than g of x, right? Like if we have this function, we know, all right, at least it's not going to be worse than g of x. We would say that f of x is big O of g of x, because g of x is, it bounds it, there is an upper bound of f of x. Sorry, it's hard to say. Okay, so that's big O. And this is, I always forget, big omega. And this is a sort of best case analysis, and it's the opposite. So if we want to know, like, we want to get our hopes up, like how good could f of x perform? What's the best we can hope for? What we would do is we would find a function g of x that is a lower bound of f of x. And if we know this function g of x, we'll know that like the best we can ever hope for is g of x. We can't hope for something better than g of x. This is the highest our hopes can go. And the last thing is big theta. So big theta is a little bit more complicated to explain, but if there's some function g of x that tightly binds, or it's a tight bound of f of x, where there's some coefficient, there's some two coefficients, a and b, that can be applied to g of x that tightly bound f of x, we'll say that f of x is big theta of g of x. And this is a sort of a stronger statement to say it's big theta of g of x, because we know it's going to fall within this bound. We can imagine that this goes out, and this goes out, and we know f of x is going to be somewhere in between. Okay, so if you've heard of these terms before, big O, big omega, and big theta, and you know what they mean, you might be a little annoyed at me for ignoring certain things. And I did that on purpose. I'm going to explain. What I just said isn't completely true, and I'm going to qualify it, but I think it makes more sense to explain it this way, where I give the partial explanation and then I go back and qualify it, rather than starting off with this intimidating definition that's hard to understand. So let me qualify what I just said. Well, actually, what I just said only needs to be true for some n greater than a. So if we looked at this, according to my old definition, g of x doesn't always provide an upper bound of f of x. Over here, in this area, where my mouse is, g of x is actually less than f of x. So it doesn't always provide an upper bound. But, I mean, who cares? Like, this little bump over here, it's not so important. So the definition of big O says that it only needs to be true for some n greater than a, where a is some integer. And we look at this area and we just say, whatever. So that's the first qualifier. And the second qualifier is like, so let's say we have this function f of x, and we want to see what its upper bound is, what its big O is. And we want to know, well, is it big O of x? And by my original definition, the answer would be no, because g of x isn't an upper bound of f of x. It's actually always lower than f of x. But the real definition of big O says that this only needs to be true for if there's some coefficient before g of x that makes g of x an upper bound. So if we said that g of x was 10x, we gave it a coefficient of 10, this would actually be up here, and it would indeed be an upper bound of f of x of f of x. So that's what the definition of those are the qualifiers to these definitions I gave you. It only needs to be true for some n greater than a, and at least for big O, there has to be some g of x where we could give it a coefficient that would make the statement true that it's an upper bound of f of x. Hopefully that made sense.